Okay, this is question 5, Homework U12, and it's a question about bearings and distances with vectors. And we've got two boats, A and B, moving with constant velocities. Boat A moves with velocity of 9 j kilometers per hour, and boat B moves with velocity 3I plus 5j kilometers per hour. So first part is to find the bearing which B is moving, and the second part of the question tells us that A starts at point 0, B 10 kilometers to the west of O, and then we're looking for expressions for A and B in terms of t, and the time when B is due south of A. So let's have a look at part A first. We'll look at these two parts separately, and we'll come on to D and E. Okay, so find the bearing on which B is moving. So we've got the velocity vector, which is 3I plus 5j. And we're going to remember that bearings are always measured from north. So we've effectively got a velocity vector that looks something like this. We've got 3I going this way, and we've got 5j going up here. And there's my j. And so we're looking at a velocity vector that's basically doing that. So we'll look at this angle here first. It's the easy one to find. And we're trying to find the bearing, which is the angle from north. So there's north there. So ultimately what we're looking for in terms of the bearing will be this angle down here. So we'll get theta first. Basic trig, tan theta is the opposite divided by the adjacent, which is 5 divided by 3, which means that theta is equal to tan to the minus 1 of 5 divided by 3, and that gives me 59.03 degrees. Okay, so the bearing is going to be the 90 degrees here minus this 59.03, which is equal to 30.96 degrees. Okay, and then come on to part B. And part B tells us that at noon, A is at the point 0, so it's at the origin. B is 10 kilometers due west of O. At time t hours after noon, the position vectors of A and B relative to O are A and B kilometers respectively. So we need to find expressions for these two position vectors, and then find the time when B is due south of A. So again, just thinking about this in terms of a diagram. So we've got effectively the x-axis running this way, we've got the y-axis obviously running this way, and so A starts off at the origin here, 0, so this is where A is going to start off, and it's got a velocity vector of 9j, so it's just simply going to move up this way along here. So its position at any point in time is going to be 9 times t times j. So there's effectively my position vector for A. Now, for B, it starts 10 kilometers to the west of O. So it might say start, say, somewhere over here. And its velocity vector is 3 plus 5j. So it's going to be moving this way. 3I plus 5j times t. So the position vector, let's just write these down now. So the position vector for A is equal to 9t times j. The position vector for B is going to be the 10 along here. Well, that's going to be minus 10. So the position vector for B is going to be the initial displacement, which is minus 10I, plus the change in displacement, which is basically going to be the 3I plus 5j times t. This 3I plus 5j times t. Okay, so basically expand this bracket out and then bring all the i's and the j's together just as per usual. So we now get minus 10 plus 3t times I plus 5t times j. Okay, so we've got the position vector and for both A and B as requested. Okay, now the question then says find the time when B is due south of A. So basically A is going to come up this way, moving faster in the y direction than B is. B is moving vertically at a rate of 5t. A is moving vertically at a rate of 9t. So basically these two things are going to end up looking something like this. So B is going to be below A. And at this point, then the I component for B must be equal to 0. So in part C, when B is due south of A, then minus 10 plus 3t must be equal to 0, which means that t must be equal to 10 divided by 3, which is 3 and 1/3. And we're looking for the time afternoon, so it's going to be 3 hours, and a third of 60 is 20, so time is 3:20 p.m. Okay, so the last part of this question is at time t hours afternoon, the distance between A and B is d kilometers. By finding an expression for the vector A to B, show that d squared equals 25 squared minus 60t plus 100. Then at noon the boats are 10 kilometers apart, and find the time afternoon at which the boats are again 10 kilometers apart. So this is basically a quadratic expression over here. So there's going to be two solutions. Obviously one solution is going to be at noon from the question, then we're simply finding the second solution. Okay, so first of all we're going to find this vector here, A to B, and so we come back to the position vectors that we found in the first part of the question. So we've already said the position vector for A is 9tj, and the position vector for B is minus 10 plus 3ti plus 5t. So in terms of a diagram, it's looking something like this. There's the y-axis, and A is going to be somewhere up here, and it's got position vector little a along here, and position vector for B is this thing along here, and we said that B is going to start at minus 10, come along here, and its position vector at any time t is this thing along here, this line along here, which is vector B. So if we want the vector A to B, the vector A to B is going to be minus A plus B. So we're after this vector here, A to B. So that's minus A plus B. So the position vector for A is 9t, so I've got minus 9t times j plus the vector for B, which is minus 10 plus 3t times I plus 5t times j. Okay, bring together all the like components, which is the j's now. So I'm now left with minus 10 plus 3ti. So that's how much I'm moving in the x direction. Minus 9 plus 5t is how much I'm moving in the y direction, which is minus 4t times j. Okay, so the distance between the two boats is that in the x and that in the y. Now we're looking for the distance between these, and to get the distance between these we just look at Pythagoras, and so we know that the distance is going to be the square of the x's, minus 10 plus 3t all squared minus, or rather plus 4t all squared, and we're going to look at then at the square root of all of that, and the question gives us d squared, or asks us to find d squared, so basically we're just going to square both sides of this equation. So the distance between them, or the distance squared between them, is going to be minus 10 plus 3t squared plus 4t squared. So simply all we've got to do now is expand the brackets out. So 10 squared is 100, 10 times 3t is 30t. There's going to be two lots of that. That gets us minus 60t. 3t squared is 9t squared. 4t squared is 16t squared. And bring together all the like components gets me 25t squared minus 60t plus 100. And that's as required by the question. Okay, the question then says in part E, find the time afternoon at which the boats are again 10 kilometers apart. So when in part E, so we've basically got D is equal to 10, which means obviously that D squared is equal to 100, squaring both sides, and essentially we're just going to equate the 100 to the 25t squared minus 60t plus 100. So we get now 25t squared minus 60t plus 100 is equal to 100. It's a quadratic. So we solve by equating to 0, so we get 25t squared minus 60t is equal to 0. Factorize the t out, so we get 25t minus 60 is equal to 0. We've got one solution here which is t equals 0, which is the condition at noon that we already expected to get from the question. And the other solution is going to be 25t minus 60 is equal to 0, which means that t is equal to 60 divided by 25, which simplifies down to 2 2/5, and a fifth of an hour is 12 minutes, 2/5 of an hour is 24 minutes, so add 2 on to noon gives me 2 o'clock and 24 minutes, so time is at 2:24.